Well, hello, Mrs. Ahmad. I hope you're doing well. Today we are going to learn about the applications of integrals. I feel like this is very important and arguably the most important thing that we've learned, the most applicable thing we've learned all year in calculus. It's very important because it puts derivatives and integrals into a real life scenarios and how we can express these products and these functions that we've learned in real life. First, it's important to look at integrals as a net change. For things that change, we can use definite integral to model real-world applications. In a first example, we see a car that travels at a constant velocity of 60 miles per hour in one direction along a straight road for 2 hours. Okay? Well, after 2 hours, we ask ourselves, how far has this car traveled? Well, we can graph the car's velocity against time. And our answer manifests itself with respect to the graph. It's perfect. Now we can see the velocity of the car and where it really goes. We can further talk about this and look at displacement, distance traveled, and the position. For displacement, it is the net change over the integral of the velocity. Now, the distance traveled is the gross distance traveled, which is the speed or the integral of the velocity to the ultimate powers. It's never negative. And then at any time position, we can just look at the position of where the function is. This is all very important for real world calculus use. Now we ask ourselves, well, now we know how to find the area under a curve. But is area always positive? Well, not really, because with respect to the x-axis, anything below that, the area is actually negative. So if we look at an entire graph, and we look from 0 to x and 0 to y, we see that between a and b, we can express this in a single integral. Now, it's important to understand that by approximating areas, we have areas, which is the integral of a graph along a function. Now, what about volumes? How do we figure out the volume of a cylinder? Well, just as area, it's always positive. So volume and our attitudes towards it should also be positive. Now, let's review how to find volume of a rectangular prism. That is a three-dimensional object with two regular faces separated by some distance. Whether it is a rectangular prism, triangular prism, or circular prism. If we can find the area of the face, we only need to multiply by the distance between the two faces. In general, the volume equals the height times the area. For some shapes, we look at the same slice points, and it's very easy. But imagine we are slicing a loaf of bread. A loaf of bread, which none of the sides are equal, they're all different curves and corners. How do we figure out the volume of this strange, irregular object? Well, we need to slice this loaf of bread up. And at each slice, we have a different face of area. One might be a function where the loaf was sliced along horizontally. For the small slices, we have to measure the thickness of the slice, whether it to be a sandwich or Texas toast. It is always delta x. And for this thickness, it forms the height, the distance between the two lines. We can slice that loaf up from left to right using a uniform delta x. By doing this, we can approximate the volume of the entire loaf by finding the volumes of each slice. The volume of each slice would equal the area of each face times delta x, where we can choose to do this 5 or 6 times. And the more we do it, the more accurate we will be. So now we know how to do area, and we know how to do volume. Well, what about arc length? It's very important that we have a pretty good idea of how far we've gone when using a GPS device. If we walk along a curved path and only have the equation of the function along whose path we traveled, it is important for us that we can use calculus to find how far we've gone. The best way to do this is the length of an arc is the function y equals f of x from x equals a to x equals b given this formula. Now this is simple enough, but something that I find more important is L'Hopital's rule in intermediate forms. So now we go back to evaluating limits. Recall the two intermediate forms, 0 over 0 and infinity over infinity, which are direct substitutions yielded either one of these results. We had to roll up our sleeves and try various algebraic methods to compute the limit. Because even though the function value failed to exist there, the limit still could, and could be anything from 5 to negative pi to 100,000 to anything it is. But so in this, with L'Hopital's rule, we're going to learn how to evaluate these limits and perhaps see many results. So who was L'Hopital and what was his rule? Well, he was a French mathematician who published this rule. Now, some call it Bernoulli's rule because he was the Swiss mathematician that founded it, but L'Hopital published it. So who really gets the credit? I say L'Hopital. Don't hate the player, hate the game. Well, what is L'Hopital's rule? Well, we look and see if there's a limit of f of x over g of x, and the limit is x to a, it yields either of the intermediate forms, 0 over 0, or positive or negative infinity over infinity. And if this is true, then the limit must equal the derivative of both f of x and g of x. This is so crucial, because now that we know that the rule works, then we can find the intermediate forms of these limits. We can find the results. We can be accurate on our AP Calculus exam. Thank you. And what I want you to go home thinking tonight, Mrs. Ahmad, is who really deserves the credit? L'Hopital or Bernoulli?